I was particularly sad this morning when I got back answering because I got this stuff from the lab. I really love going to, and I just got canceled my other things and I'm very, very sad that I missed my 7:50 lab this morning. I guess students were also equally sad. Okay, so I think what I'm going to do on WebAssign, if you'd like, you email me which WebAssign questions you want me to talk about. Email me your question and a brief description, which question it is and what your question is about it, what you've done already, what you're stuck on, something like that. And I'll take a few of these and solve it and post a video about them, okay? And that way we'll make up for lost time. Anytime I got to go on. If I have more time for WebAssign questions later, I'll do that. But in case some of you need help now, you can go ahead and email me. I'll try to do that sometime soon, okay? But I have a couple topics we need to wrap up today. So the Lotus Friction, I want to do one more example on friction in planes. Really two examples. First one's this. So I've got a plane and angle theta. The question is just this. As you slowly raise the plane, suppose this is like you can move this, it's a board, it can be raised and lowered. And let's suppose that the coefficient of static friction here is 0.7, and the coefficient of kinetic friction is 0.2. And the question is, if the box starts at rest like this, right? And as you raise the angle, at what angle does the box start sliding? Right? And then, second part of the question, what's the acceleration of the box after it starts sliding? Okay? Assuming you fix that angle. So, again, you start at theta equals to 0, then increase theta until the box starts sliding. You fix theta, and then what is the acceleration of the sliding? So there's two questions. What is that theta naught, let's say? Or we call it theta s for sliding. So. All right. So what do? We draw the free body diagram. And I'm just going to go ahead and get to the point here. There's a normal force like this. Right? There's part of gravity which is perpendicular to the plane, which is this case, which is what? mg, is it sine theta? Is it cosine theta? What's cosine theta, right? The force of gravity down plane, this guy, mg sine theta. And then, of course, you've got the force of friction, which is going to be opposite the potential motion at the start. And so that's this way, right? Force of friction. Which, by the way, is mu times the normal force. Where, of course, either that's mu sub s or mu sub k, depending on whether it's moving or not. If it's not moving, in the static case, right? If it's moving, we're in the kinetic case. Are there any other forces? I think the wind resistance, okay, we're neglecting that. You might ask me, what's the mass? The answer is, I don't care. Doesn't matter. Don't need to know it. You can still solve the problem. See how? Okay, so Newton's law. First of all, the perpendicular direction, we have 0, right? 0 is equal to, the normal force up, right? Minus mg cosine theta. So that tells me then what? It tells me the normal force is mg cosine theta. Which, by the way, then tells me the force of friction is mu mg cosine theta. That's nice to know. The parallel case. Okay, so there I have MA. right? We're updating the acceleration. Let's just say acceleration down in the plane is positive, okay? If I say that, then we got what? We got mg sine theta. What else is parallel? Oh, the friction force, right? Minus mu times, well, minus the force of friction. It's minus mu mg cosine theta using that right here, right? Some words are helpful. Okay, so before it slips, right? Or say right before it slips. Right before, I mean just immediately before it slips. We have acceleration 0, right? Is equal to what? It's equal to mg, and it's just before I could just replace theta with the sliding theta, right? And in that case, which mu should I use also? We're in the static case, right? So I should go to the use of S there. You see, you might have complained you didn't tell me the mass. I don't know how to solve this problem. I can't find the weight. I can't find the force of friction. I can't find anything, but it didn't matter, right?
Because the m's cancel.
Right, everything's proportional to m. So you can divide by m. I suppose I'm supposing that I do guess in all honesty I am under the assumption that the mass is not 0. But seems like a fairly reasonable assumption for classical mechanics. Oh,
Gravity goes away.
G, yeah. Interesting, gravity goes away. I guess this problem would actually be the same if I asked it on the moon. Right? Didn't matter that we're on Earth. As long as your where gravity is relatively constant over the scale of the experiment, right? If gravity had some variation, some non-trivial variation over the size of the motion, like say on the, I don't know, like near an event horizon or something, someplace where you got those tidal forces or something like that. But anyway, we don't know. Ignoring singularities and such, that's fine. And then, what we got? Well, oops, let me be green. So check it out. I got sine theta s over cosine theta s equals what? Mu sub s, which is what? 0.7. So the slipping theta is inverse tangent of 0.7 for this problem. Can you guys calculate that for me? Like 35. 35. Thank you. Does everyone agree? After all, as we discussed, science is based on consensus. Don't forget that. Is there a consensus is 35 degrees?
34.99.
34.99. Okay. We'll let it slide. 35. See, Egbert has asked me that I make puns today, so I did my part. My best puns are unintentional, though, like that one. And then what is acceleration? So when it slips, mu is equal to mu k. And then we just go back up to this equation and solve for A. A is equal to G times, I'll factor the G out, right? Sine of the slipping theta minus 0.2 cosine of the slipping theta. So G times the sine of 35 minus 0.2 times the cosine of 35. What do we got? What is it?
4.01.
Wait, 4.01? Oh, you're multiplied by G. Before you multiply by G. I was guessing it's about 0.4 G's. What? What's this number? I mean, underlined twice. What's this number underlined twice? Sine 30. What's that? 0.4097, okay. So 0.0, about 40% of gravity. Right. Or, like you said, 4.1 meters per second squared?
4.014.
Was it 4 point what? 4.014?
1,000.
That isn't right. Oh, okay, I got you. 4.014 meters per second squared. Okay, yeah. That makes sense. G's a little less than 10. So, yeah, okay. So guys, when you have a problem with friction, and there's some you don't know it's moving or not, you have to analyze possibilities. Like, is there enough static friction force to keep it in place? Is there not? If there isn't, then you're in the kinetic region, and you kind of have to reason through that for a given problem. There's cases to consider. All right. My next example, a little bit quicker. Suppose you got two boxes, M1, M2, like so. There's a pulley. Oh, I don't need two boxes, just need one, sorry. So, one box will do. And then I've got, let's see here, suppose I got M1 hanging over here, and M3 hanging over here, table. And let's suppose it's moving, all right? And suppose the kinetic coefficient of friction is 0.5. All right? What's that?
That's the kinetic?
Yeah, suppose the kinetic coefficient is 5 for this, between the table and M2. So, I mean, I'm assuming that M1 is, is greater than M2 plus M. I mean, I choose M1 large enough so that the motion is this way, okay? Just let me explain that. Do you want me to make up some numbers? I can make up some numbers here. How about M1 is equal to 100 kilograms. M2 is equal to 10 kilograms. M3 is equal to, say, 20 kilograms. There you go. I think I'm pretty sure that those numbers will actually make it move to the left. Right? Yeah. Okay. So then the obvious question is, what's the acceleration? All right. So there are 3 Newton's laws to think about here. I'll do the 2 kind of silly ones first. First of all, you've got the tension. Let's say P1 that way, right? And you've got M3G down, right? On the other side, for M1, if you look at that, you've got the other tension, which doesn't have to be the same, it's not the same rope. All right, so tension 2 goes up and M1G goes down. Those do not have to be equal because the system is accelerating, right? In fact, the string is not stretching. These things are connected, like the motion of M1, M2, and M3. They're all at the same rate of acceleration, right? They're all together in their motion. So they share the same acceleration. That's just a geometric observation. And so there's that. And now finally, the interesting one. Here, let's see here. You got the normal force going up, right? You've got what? You got what did I just say? M2G goes down. But then what else do we have? Yeah, friction. Which way does it go? Yeah, right. It does not make the thing speed up, so let's make it go opposite the motion. Very good. Okay, so force of friction. And so the force of friction is what, by the way? Force of, well, let's see here. Perpendicular direction for M2, we have 0 is equal to the normal force minus M2G. So therefore the normal force is equal to M2G, which tells me the force of friction, which is, of course, coming from the second mass, this M2 up here, right, is what? It's 0.5 times M2G, right? Okay. So there's that. There's that. That's good. Oh, goodness gracious. There are 2 more forces on M2. What have I neglected?
T1, T2.
How about the tensions, maybe? So T1, T1 goes this way, right? And T2 goes this way. Am I right? Okay, you're not right. Okay. I hope I'm right. I'm pretty sure. Let's go. Okay, so, all right, so we've got 3 Newton's laws. I'm going to write them here. First of all, M1A is equal to, let's see, A positive was this direction, right? So that makes M1G positive minus T2. M2A is the kind of interesting one. M2A, at acceleration, let's see what do I got going on here. T2 is in the positive direction. And I've got the force of friction. So minus 0.5 M2G this way. By the way, you notice I'm not putting in numbers yet. It really does not pay off to put numbers in too early in these kinds of problems. Because then instead of writing what I'm writing, you're writing level kilograms. And what if instead of being, 110 and 20, what if I had given you 55.7? I mean, all of a sudden you've got all this clutter of numbers, you can't see what you're doing anymore. It pays off to be symbolic for a little bit, if you're careful. Payoff is big. I mean, if you're really careful, you may inadvertently solve the problem for all possible sets of values rather than just the ones you're given. Right? Certainly it's better to solve infinitely many problems than just one. The extra credit for it. Extra credit for it. Yeah, that's possible. Where was I? Oh, what other forces there on M2? I got my T2. I got my T1. Oh, I don't got my T1 yet. So minus T1. Is there anything else horizontally on M2? I think that's it. Three-body diagram helps keep us honest. M3A is, okay, so T1 is in the positive direction this time, and minus M3G. All right, we've got 3 equations and 3 unknowns. What are the 3 unknowns? Tension 1, tension 2, and the acceleration. So, since we're after the acceleration, you want to do algebra to eliminate T1 and T2 basically, right? So, simple thing I see to do is just take these 2 equations and add them. If you add those equations, you get M1 plus M2 times A, equals to, the T2's cancel, M1G, what do you get, minus 0.5 M2G, and then minus T1, right? The T2's canceled, you notice that? But if you still got this pesky T1, but hey, the natural enemy of that is this equation down here, right? So you just take this equation and put it over here. M3A is equal to T1 minus M3G. Then what do? Take these equations and add them once more. What does that give you? M1 plus M2 plus M3 times A. The tensions cancel, and we're just left with things we care about. M1 minus 0.5 M2 minus M3 all times G. Tensions canceled. I factored out the G. And so there's our answer. The acceleration is equal to M1 minus 0.5 m2 minus m3 divided by the sum of the masses all times g. Now, of course, I didn't have numbers here. I guess I should put them in.
Or you could remove numbers.
What's that?
Or you could remove numbers.
Just erase the numbers. But in some sense, this is a friendlier problem if I don't put numbers in on the test. In some sense. In another sense, it's punishing because unless you can find this algebraic solution, you're kind of stuck. If you think about physics step by step rather than holistically, you're pretty good at this problem, right? I don't think you know. I do both. I mean, there's a mixture of the test. So anyway, so M1 was 100, so I got 100. The kilograms will cancel, so let's just forget the kilograms. 0.5 of M2, well, that's just 5. M3 was 20, so minus 20. Divided by, that looks like 130 to me. Mg, so the acceleration is something like
5.654.
5.654. Is that meters per second squared or is that feet?
What's meters per second squared?
Okay, I'll take it. Thank you. Any questions about that? No? All right. So, I want to talk to you a little bit. I have two more things remaining for today. The one is terminal velocity, and the other is springs. All right. Now, I will tell you part of. We have a lot more to say about springs as we study energy and work. So, come Friday, I'm going to start talking about the line integral and work and conservation of energy and all that. So, it's going to be a pretty big change in the story we're telling in some sense. I mean, what I'm doing today is almost completely disconnected from what I'm doing Friday in terms of solution technique. All right, so it's a big change. But these two topics still belong here. So the first is terminal velocity. I mean, well, I don't know if it belongs here. You could do it elsewhere, but I'm going to talk about it here. Since you, after all, do have homework on it, so it would be nice if I talk about this a little bit. What is terminal velocity?
Do you think you'll reach?
What's that?
You can reach terminal velocity.
You never know what you
I don't know anybody in DEqns. I wish I did.
That's house.
House cleaning, yeah. That's not the kind of terminal velocity you're talking about. Let's see here. So if you have something falling, like, I don't know. Yeah, and he's falling. There are basically, and now finally we're not ignoring air friction, okay? Yeah, finally at last. All right. Well, there are two things, really. Think about it. You got the force of gravity, which obviously goes down, okay? And then you have the force of air friction, which goes which way? Up, yeah. Since your motion's down. Now, if you were, if I happen to be talking about, you know, if I had, I don't know, and I mean, suppose you had a giant spring, compress it, right? The cat on top of the spring, and then you hurl the cat upwards into the sky. I don't know, maybe call it or whatever. In this motion, the free body diagram is a little bit different, right? In that case, what's the deal? You have the mg this way, but guess what? Force of friction, also that way. So the force of friction isn't always opposite gravity. Sometimes it acts in concert with gravity, at least for upward motion, right? Now this force of friction is not the one we've been talking about earlier today, right? This one is some sort of hypothetical velocity-dependent friction that depends on the particular nature of air, the particular velocity, blah, 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 blah. So for example, and these are really just hypothetical examples, suppose the force of friction happens to be something like 2.0 units, we'll figure them out, v squared. So if I put units here to make it right, let's say alpha v squared, what units should alpha be? It should be something like a Newton divided by meters per second quantity squared in order to make this reasonable. Because if that formula is reasonable, if it's dimensionally consistent, it must give me back newtons. The only way I can get newtons from such a formula is if I multiply a velocity squared by something which divides out the units of velocity squared. So that would be the units for alpha. Assuming alpha is some constant. I'm letting alpha be the unit. This unit. What is that? You guys told me a kilogram per meter. That's a kilogram meter per second squared times meters squared over second squared. So you said it was what? It was a
Kilogram meter. Divided by meter.
kilogram meter. Oh, a kilogram over meter.
Yeah.
Yeah. Okay. Okay. So there you go. Then the question would be, for a cat with mass, I don't know, 2 kilograms. What is terminal velocity? Right. And suppose cat dropped from Empire State Building. All right. Now that we've got the circumstances clear, this is a happy example. So what's the terminal velocity? So the terminal velocity is that velocity in which the cat stops speeding up. All right, it's the highest velocity you can reach because there's some velocity, right, where mg down and the force of friction up balance. All right, when that happens, the acceleration is 0. It's falling down, right? But it doesn't go faster. Let's see. So to find that, we just say the acceleration is 0. To reach terminal velocity, that means it's not speeding up anymore. Its speed is not changing. So 0 is equal to mg minus 2.0 alpha v squared. Let's see here, m was what? So v squared was equal to mg divided by 2 alpha, which is 2.0 kilograms times 9.8 meters per second squared. Sorry, it's markers no longer like 2 times kilogram over meters, making sure my units work out. Kilograms cancel, and so I've got v squared is equal to, as it turns out, 9.8 meters squared over second squared. So the terminal velocity here would be the square root of 9.8 meters per second, which is what? Which is square root of 9.8, like 3.2. So what do you got? 3.13 meters per second is the terminal velocity. This isn't a happy example, but I think the cat will survive that.
That's why cats can survive such long falls, as they do.
Yeah, I don't know. I just made up that alpha. This isn't really a physically reasonable example. Where does this coefficient? This coefficient is like a really complicated thing. And is the velocity dependent on is the friction dependent on the square of the velocity? I think I told you guys, I don't know. I've seen papers that say it's linear for certain ranges, it's quadratic for other ranges, it's cubic for other ranges, some sort of probably matters are their clouds. The actual coefficient for a cat would depend on whether the cat was like diving, paws together, like it does. I don't know if there's a cat doing that, but I mean, you guys have seen action adventure movies. You know what happens if you you do this, then you kind of go slower. If you try to make yourself smaller, you make the cross section of air hitting you smaller, you go faster. So terminal velocity depends on your shape, right? Ultimate example of this being one of these guys, right? You got one of these things called a parachute, then your terminal velocity is considerably lower, right? Because the force of friction on the air puts a lot more force of friction on a parachute than it does a person, because there's a lot more surface area to catch the air, right? So anyway, how do you do your homework? You set gravity minus the force of friction or plus the force of friction equal to 0 and solve for v. Whether it's minus or plus depends on whether it's going up or going down. Whether the force of friction and gravity are going in different directions in the same direction. That make sense? I actually have an example, yeah.
So in a situation where it's going up, is there only going to be one point in time in which it reaches terminal velocity? Depends on how you define terminal velocity. Because it's going to continue decreasing in velocity after that one moment.
It should be like a 0. Well, you need to terminal velocity would be your maximum attained, which would be constant until acted on by something else.
Yeah, you're right. I shouldn't really say, using the same term is a little bit wrong. I really should say it's the maximum velocity in the upward motion. Yeah. Yeah. Because you're right, it slows down. Yeah.
Is that going to be the moment it leaves the spring, per se? Because it's only going to decrease in velocity from there. So
yeah, I tend to think for the spring, my intuition is that for the spring, it will not reach terminal velocity on the way back down. Assuming the same velocity dependence going up and down.
Yeah, unless it's like spring on the edge of a cliff and you...
I like
2 degrees to the right.
I like the way you think. Yes, with the spring on the edge of a bottomless pit. So springs. Let's talk about springs a little bit. Oh. Do I have time? I have time. Let me work one more example of terminal velocity. Suppose the force of friction is equal to beta v. Solve the equation of motion. I'll go somewhat quick through this because I'm going to use some math that you're not supposed to know. Hope you can forgive me. And suppose we have mass m. So basically what I'm faced with here, and that's the only thing, okay? And let's say let's draw a picture. So we got mg this way, and I'm assuming that the force of friction is that way, okay? So apparently I'm assuming the motion's downward, all right? But I guess if I write this, I'm also, okay. I gotta make some sign choices here, So m dv dt would be ma, right? I gotta make a choice. Do you guys want down to be positive or down to be negative? Down. All right, down positive, I guess. I'm sorry, I've offended half of you. Down is positive. I like it. You guys have your own mind. It's good. It's good. So down is positive. If I say that, I write md v dt. Well, first of all, mg, positive, right? Force friction, on the other hand, here's the kind of tricky part. Down is positive. That means v is positive, right? Downward is some positive velocity in this case. So I guess I just get to do minus beta v, right? Yeah. Okay. Yeah. Now the question is, can you solve that? Well, if I divide by m, what I have then is dv dt. Let's see here, add v to the other side, plus beta over m times v is equal to g. There's a pretty decent chance you'll learn how to solve this in calculus 2 here. This is called a linear ordinary differential equation. You can solve this by something called the integrating factor method. So I can look at this and tell you the integrating factor here is the exponential beta t over m. And if I multiply this equation by e to the beta t over m, which is certainly fair because that's non-zero, I haven't changed anything, right? Then, behold, the magic of the integrating factor. This is reverse product rule of ddt of e to the beta t over m times v. And on the other side, you've still got this handy dandy g e to the beta t over m. Integrate both sides. Integrate both sides, and what you get I integrate both sides from, say, time 0 to time t.
What happened to the dv?
This is the product rule in reverse. Differentiate this to get back to here. So if I integrate both sides from, say, time 0 to time t, I get the net change theorem on the left-hand side. So at time t would give me e to the beta t over m times the velocity at time t, and then minus, well, e to the 0, velocity times 0. On the other side, if I integrate from, say, time 0 to time t, I'm feeling guilty for using bad notation. I'll put a t-bar here, e to the beta t-bar over m d t-bar being a dummy variable of integration. Okay, that's an exponential of a constant, so you just flip the constant over. You go mg over beta e to the beta t-bar over m. You evaluate that thing from 0 to t. That gives you mg over beta e to the beta t over m. E to the 0 is 1. Okay, great. And now I can just solve for v of t. V of t, the velocity at time t, is equal to the velocity at time 0, which I'll call v naught, plus mg over beta times e to the beta t over m minus 1 parentheses all of this junk times this, the inverse of that, which would be e to the minus beta t over m. That's what I get finally. Pretty nice formula. I get v naught e to the minus beta t over m plus, and then parentheses here I get mg over beta minus, let's see here, mg over beta e to the minus beta t over m. There you go. Actually, with calculus 2, you can solve these kinds of problems with friction. They're not that bad. Now, it's fun to think about what happens as time goes to infinity. What happens as time goes to infinity here? Let's see. These exponentials, I'm assuming that beta and m are positive, right? So that makes this an exponential with a negative argument. Those go to 0 as time goes to infinity.
Yes.
So death to this, death to that, all that survives, mg over beta. But check it out. That's exactly what you would have got if you just took this and set it to 0 from the start and just solve for b. See? mg minus beta v equals to 0. v equals mg over beta, terminal velocity. Solution by physical intuition. Solution by math. So there's a big difference, right? Math tells you how it gets to the terminal velocity and so forth and so on. It can quantify how long it takes you to get to 99% of the terminal velocity, blah, blah, blah. Right? Physics just tells you what it is. But I think you're happy that I've asked you about this in the homework. I don't think I asked you about that. You should want to learn that as engineers, though, right? Yeah.
That's
Basic application of calculus to real-world physical problems. Like, us humans have known this for about 400 years, give or take. You'd like to be part of that class of humans at some point. Just saying. Oh, okay. Springs. There are other ways to solve that differential equation. I think you can also solve that differential equation by just separation of variables. But anyway, could be wrong. Springs. Basically, the point here is if you have a spring, and let's talk about it horizontally. So we're basically not thinking about gravity here, okay? So you have a spring, and you attach it to a box, say with mass m. Spring constant has spring constant k, right? There are basically 3 cases that you have to think about. Okay, there's compression, equilibrium, and there is stretching. Or stretch, let's say. So compression would be when x is less than 0. Equilibrium would be when x is equal to 0. Stretch would be x greater than 0. And so just to, so I can draw a picture. So I'm going to try to draw a common x equal to 0 for all 3 of my pictures. Okay, so when it's compressed, what direction does the force go? You compress the spring, the spring pushes back that way in my picture, right? So the spring force would be like this. When it's at equilibrium, that's the place where the spring is just sitting there. It's neither compressed nor stretched. It just sits there, minds its own business. The spring force is 0. When it is stretched, on the other hand, the spring is trying to pull the mass back to that equilibrium position, right? So there, the spring force points to the left. Right? So given my system of labeling, there's a simple formula to get all of three of these cases all at once. It's called Hooke's law. Hooke's law is very nearly true for a lot of springs that you can construct from materials available to you on this earth that we inhabit. So the force of the spring. Now, of course, this is an approximate law. I mean, this is, but it's pretty true for some springs we have in the lab, for example. There's a deeper comment to make, though, that we see something like springs appear in physics everywhere. Physicists will say something like, all of nature is built from harmonic oscillators. Well, spring is a harmonic oscillator. Now, they're talking in a more abstract sense. They don't really mean that nature is made of springs. They mean that the laws of physics are like springs in some approximation. That comment will make more sense in about 2 lectures. Anyway, so force of the spring is equal to minus kx. So you see what happens with this formula. If x is less than 0, minus gives you plus, the force goes to the right. If x is equal to 0, 0. And finally, if x is positive, then this is negative, which means that the force goes to the left. It's our convention, right? Yes?
X is relative to equilibrium,
Right. This is the right. Indeed. So, for example, if I tell you a spring has a force of 10 newtons when compressed, 0.5 centimeters, then what is K? That's pretty easy. What is K? Now, this K, by the way, is called the spring constant. It's a really inventive name, right? Yes, the spring constant, which is the constant associated with the spring. Simple enough? Yes, I mean, yeah, sorry. Come up with a more interesting name for this K. I don't know, but whatever. So here you go. 10 newtons then.
We make that meters.
Centimeters. Compressed. Now I'm ignoring the signs here, right? So it's 0.5 centimeters times K. Yes, in fact, so that means K is equal to 10 newtons divided by 0.5 centimeters. That's 10 to the minus 2, right? Meters. Let's see here. So in terms of, usually you want to give it in terms of newtons per meter. I think that's 200 newtons per meter if I haven't made a mistake, which is, well, anyway, you guys tell me if I made a mistake. Am I wrong? My logic was 10 divided by 0.5 is 20.
The big thing I think is if it's pulled back 0.5 centimeters, then you've got to put the negative on the bottom. If that makes any sense. Like have negative centimeters when you move everything over.
There, I fixed it. Sorry. I'm not trying to worry about the sign right now. That's more of an issue for us. This problem. I appreciate what you're saying, but not what I'm trying to get at the moment. 2,000?
I get you.
Oh yeah, 20 times 200 is 2,000. Idiot. Not you, it's me. There. So. Yes, beware the centimeter versus meter issue with these problems. It is a persistent source of doom. All right, well, I have more to say about springs once we know more about energy, but that's about all I got for you right now.